the area that is affected. How do you mean? Why is it 2? On both sides, you cheeky sort. Okay, let me quickly draw single shear and double shear. Okay, so I will ask you questions like this. Okay, so for single shear, you have 2 plates and you have a bolt or a pin, whatever. Right? And this is plate number 1. This is plate number 2. Okay. So where is failure going to occur? Exactly where? If shear is going to fail, if failure is going to occur, failure is going to occur over here. Failure location. And it's the cross-sectional area of the bolt. So this is what we call what? Single shear. We clear? Double shear, as you can see now, now you have 3 plates. 1, 2, and 3. By the way, 303, last 2 lecture, you're looking at the gorilla that will be teaching you on mole circle. Are we clear? Do not skip class. Okay, mole circle is very important. Ask him, is mole circle important? Okay, so don't rely on the videos. Come for my lectures, last 2 lectures. I'm going to miss my daughter, but it's worth the sacrifice. So now you have where? 3 plates. Agree or disagree? So we are going to assume that failure will occur at the top and at the where? At the bottom. So this is what? The top and the bottom is what we call what? Twice the what? Twice the area. Nothing to do to divide the force by 2. It is what? Twice the area. Are we clear? So from here, if I were to ask you that calculate the shear stress that's acting on the bolt, so assuming that the area or the radius of the pin, okay, is equal to 20 millimeters. So the shear stress is the force that you calculate 299.5 divided by twice the cross-section area, pi, and the radius of the is 0.02 squared. So this will give you a figure of 299.5 divided by 2 divided by shift pi divided by 0.02 divided by 0.02. It will generate a shear stress of 119.167 times 10 to the power 3 Pascal. Okay, so this makes it a full circle. It's not like, why are we learning about acceleration? Why are we learning about forces? There you go. This is the purpose. At least now we can do something that is what? Swinging. We clear? Question, anyone? Are we okay? Okay, right. So the next problem that I'm going to do, now this problem is, it's not impossible, okay? But the problem with this problem is very abstract. Okay, it's one of the difficult problems. I did not say it's coming out. I'm just saying that it's one of the what? Difficult problem. And a problem like this will make you understand your fundamentals better. Okay. Now, before I go on, a problem like this is very extensive. Yes or no? Right? The problem part is make sure that you have to make sure that you use the right what? Mass moment of area. We clear? Okay, if you use the wrong one, okay, you will not get 0 mark. 1 mark will be deducted. Okay, but you have to be very precise in how you do this. Are we clear? Okay. Right. So the problem that we have now. So what you see down here, I want to expose you to a lot of problems to see different approaches. Okay. Now, before I go into this problem, again down here, right? If you were to take your moment at point G or GR over here, your answer will also be the what? Be the same. Are we clear? Okay, I want you all to have that level of confidence rather than not so clear about that. Slender rod, length L, and mass is released when theta is equal to 0. Determine as a function of theta the normal and the frictional forces are exerted by the edge of the rod as it falls down. Okay. At what angle does the rod begin to slip? If the coefficient of friction at A is equal to mu. Okay. So remember, we had two conditions, right? Remember when I started all this, I mentioned that we had two conditions. Okay. When there's no slip, what will happen? Can someone look for me the formula when it's no slip? When it's no slip, what will happen? A is equal to what? Yes or no? Right? And then FR is not equal to what? Okay. You just need to remember this. Okay. When there's slip, when slipping start to occur, then acceleration is not equal to alpha R, but FR will be equal to what? Are we clear? Yes. Capital R. Oh, frictional. Oh, sorry. Okay, let's not call R. Okay, let's call it FF. Okay. So FF is the frictional force. And Rn, hey, Rn, come on, is the normal force. Okay. So again, once you see a problem like that, the most important thing is to draw the free body diagram, and the free body diagram is so straightforward. Now, and as you can see, what we have down here is rotation about a fixed axis. Okay, you can see that this problem is rotation about fixed axis. The problem that we're going to do later on, which is holy shit, is also what? Rotation about a what? A fixed axis. Are we clear? Okay, so this problem that we will do probably on Thursday, and what we have over here, the approach is very similar, and I want you to look at the trend. Okay, so from here, we are going to start drawing the free body diagram. Now, when it's rotation about a fixed axis, we are going to use what? The N and what? Okay, we are going to use the N and T axis. Are we clear? Okay, so let's start constructing the N and T axis. So like before, so this is our force. So how will this beam be falling? Anyone? Clockwise or anti-clockwise? Clockwise, okay. So when it's clockwise, right, we know that this direction will be our alpha. So when that's the case, over here will be your what? T, over here will be your what? N. Are we clear? The N is always pointing towards the center of rotation. Okay, so N always pointing towards center of rotation. And from there, we start to draw. So this is our G, which is our center of gravity. So we know that over here coming down, right, is our what? Mg. Okay. And then we know based on vector form, this angle is your theta. So over here is your mg sine theta. This arrow over here will be your mg cos theta. Okay. We are going to have Na over here. And then we are going to have F over here. Okay. Okay. Right. So that is our forces. Very straightforward. Then the next thing we come to do, I can draw a bit smaller. Is our kinetic diagram. Smaller does not mean it's not important. Okay, I'm just. So this is our kinetic diagram. Right. Same thing. This is our T. This is our N. And the center of gravity. And when we know that there is over here is our M, A, G, T, right? And then pointing towards the center of rotation, if M, A, G, N, sorry. M, and this thing has a rotation. The rotation over here is I, G, alpha. Now this thing can look pretty confusing now. Okay, so the formula sheet will provide you with this sort of information. Okay, so we know that Ig is equal to 1/12 ml squared. We just came from there, yes or no? Right? Yes. Yep, no, it should, but I make my life easy so that all components will be on the N and T orientation deliberately. So I no need to sine, cosine, theta, you know what I mean? Right? That solve the T and you know what I mean? Okay. And then we are given, or these formulas will be given that AG, okay, so I do apologize. So this will be equal to 1/12 ml squared. Okay. And then from here, we know that our AGN, okay, will be equal to omega squared R. So omega squared R, so this is equal to omega squared L/2. Okay. Because it's taken at the center of gravity, we know that this distance from here to here is equal to L/2. Okay. And then finally, we have AGT, which is equal to alpha R. Okay. So this will be equal to alpha L over 2. So if we were to go back to the question, we will ask this very important point, right? At what angle, hey, come on. At what angle does the rod begin to slip if the static coefficient is equal to mu? Okay. So if you look at this, right, the final answer should be equal to theta as a function of mu. And what is this value? Okay. So that is how your final answer should look like. Okay. So we know what is our variable. We know what is our response. Okay. So from here, this is I think the most important part is the analysis. This is the analysis that you need to know. Okay. And the rest over here are all analysis. Okay. Then is forming the equation. Forming the equation, all of you are, I think, are really good at it now. Okay. So next, we form the equation. It's like 2P04 when you form the equation, except nothing goes to 0. So we know that coming down in this direction, summation of forces is equal to T. So this is equal to M A G T. Okay. So from here, so we say coming down is positive. So we have minus NA plus by mg cos theta. This will